nor the curvature of the Earth. So we've actually talked about this picture right here before. If we're launching a projectile farther and farther and farther with more and more power, eventually the curvature of the Earth comes into play. And if we put even more power behind it, the ball or whatever it is lands farther and farther and farther and farther until eventually we put so much power behind this thing that the planet is falling away from the cannonball or whatever it is at the same rate that the cannonball is trying to fall back to Earth. And if that happens, then the cannonball is perpetually falling. It never lands back on Earth.
So that's what we call as an orbit.
That's what we call orbit. That's right. So if the launch speed, v sub I, is large enough, there comes a point at which the curve of the trajectory and the curve of the Earth are parallel. Making a closed trajectory is the official language there. And that type of trajectory is called an orbit. An orbiting projectile is in perpetual free fall then, directed toward the center of the planet rather than down. So now it's in like a circular motion, which is why this is relevant to the discussion in this chapter. So it is still circular motion, but now it's called an orbit because it's going around the planet. And then this is caused by gravity. So we're talking about orbit today.
So I got a quick question.
Oh, yeah, sure.
So since mass really doesn't have a whole lot of an effect.
So now in uniform circular motion, we have acceleration equals v squared over r, of course. So in orbit, the acceleration is due to gravity, though. So we have acceleration equals v squared orbit over r equals g. So then Earth's radius on average is the radius equals capital R sub e. And that is 6.37 times 10 to the 6th meters for Earth. Then the velocity of the orbit equals the square root, if we're solving for the velocity, the square root of g times the radius of the Earth, and that works out to 7,900 meters per second, which if we do our little conversion is approximately 18,000 miles per hour. So if you want to put something in orbit, you're going to be going around 18,000 miles per hour. Orbit, remember, just means the Earth is falling away from the object at the same rate that the object is moving.
Does it matter how far you are?
And so that's why I just said that. We don't have a radius away from the Earth. We just are using the radius of the Earth, right? So how far off of the Earth are we at this point? How far?
Earth's radius.
Earth's radius. Yeah, we're not off of the Earth's surface. This is on the Earth's surface. So if you want to like launch something horizontal to the Earth's surface on the Earth's surface, it'd have to be going 18,000 miles per hour.
And you have to deal with things like drag and friction.
Yeah, then there's exactly.
And then there's people that might hit.
So it's not going to work, right? But theoretically, that's how fast you have to be going. So now we can use the velocity of the orbit to calculate the period of the satellite's orbit. So we have period, remember we use capital T for period, equals 2 pi r over the velocity. We have that formula. Equals 2 pi square root r over g. So for an Earth skimming orbit, like we just calculated, we would have T equals 5,065 seconds, which we can convert to something that makes a little bit more sense, 84.4 minutes. Okay, so if we did this, we launched something at 18,000 miles per hour on the Earth's surface, it would take 84.4 minutes for it to come right back around and hit us in the butt, okay?
Can you imagine going that fast in like the day and night cycle?
One terrible spanking.
So actual satellites need to be a little higher, of course. We need to get out of the way of trees and whatever else, plus the drag of the atmosphere. So the International Space Station, ISS, is 250 miles above the Earth's surface, which actually really isn't that high when you consider other satellites and the things that we have up there. Only 6% greater than the radius of the Earth, 250 miles up. There really isn't that much. So this gives the International Space Station an orbital period of 87 minutes if you use what we've been calculating by our equation. So the actual period of the International Space Station is actually about 93 minutes, meaning it orbits the Earth more than 15 times per day. So, by the way, you can see the International Space Station. Have you ever seen it?
Yeah, like at night, and you see it.
You can see it kind of streaking across the sky at night. It looks like Venus. It's about the same brightness as Venus. You can usually see it just after sunset. Sometimes later than that. If you catch it just right, you can see it. You can see the sun actually setting on the International Space Station. It is very, very bright, and then it kind of goes dim. But it moves very, very quickly across the sky. And then if you look at it, you're like, oh, what is that? It looks like a plane, but nothing on it is blinking. There's no blinking lights, and it's moving way faster than a plane. So anyway, you can kind of spot it sometimes. Also, there's apps that you can get that tell you when it's going to fly over. So weightlessness. Do we have weightlessness in orbit? In other words, is there gravity in orbit? The answer is, of course, yes, there is. It looks like there is not. But we just talked about the fact that a projectile that is in orbit is actually being pulled back to Earth at the same rate that it is flying around Earth. So there must still be gravity, which means that objects in orbit must not be weightless. Okay, so in orbit, there is still gravity. Very important. It's just a misconception that there is not. So it's just that the object is a projectile in perpetual free fall. So it seems to the observer that the object is weightless when actually the object and its surroundings are in a state of free fall at the same rate, falling together along the same trajectory, which just means it's in orbit. So the object itself in that situation has an apparent weight of 0. This is key. Apparent weight, not real weight, relative to the system that it is in, because it has no contact forces acting on it. Okay. So let's take a look at this. A satellite is in a low Earth orbit. Which of the following changes would increase the orbital period? What do you think? The key is always there must be some concept or formula to look at or think about. And in this case, there's a formula to look at and think about. So what are the variables here? We're talking about period, right?
Yeah.
That's that guy. And we want to increase the period, okay? So all of these say increase here, right? So if I increase the mass, there is no mass in this formula, so it can't be A. Increase the height of the satellite means increase the radius. If I increase this number right here, does the period increase or decrease? It increases. If I increase gravity, does this fraction grow or get smaller?
Smaller.
It gets smaller, which means the period will increase or decrease. It decreases, not increases. So the answer must be B. Okay. A concept or a formula to think about on these problems is how you want to always go. So that's the answer, B. Nice job. Okay, now the orbit of the moon. So the moon's orbit is approximately circular. So we'll call it circular then. At an average distance of 3.84 times 10 to the 8th meters, calculate the moon's orbital period.
Oh, I got this.
You
Use
do?
that same equation.
The same equation.
Yes.
Okay. So
T
what do you mean by the
pi.
same equation?
T equals 2 pi square root r over g.
Oh, okay. T equals 2 pi square root. What's the radius?
It'd be 3.8.
Yeah, it's the number they gave us. 3.84 times 10 to the 8th meters divided by?
9.8 meters per second.
Okay.
Oh, no.
9.8 meters per second squared.
What? Because it's
Why-
orbiting around.
It's orbiting around Earth, so.
The Earth's
Oh,
gravitational pull.
okay.
Okay, yeah, makes sense. All right, so
I thought it was
And Michigan
For
won
some
last
reason,
night.
I thought it was like an astronaut orbiting around the moon.
Oh no, the moon's orbit around Earth.
Okay.
What is
So, but
Michigan won last night.
They did.
is
Go
that
Blue.
perchance
Yeah.
while you're wearing a hockey jersey?
Well, this is the
Only Michigan.
loudest and proudest jersey I have.
It's hockey though, isn't it?
It is hockey. Yeah. What do we got?
6259.69. So we can go what?
Did you square root it?
Yes. 3.84 times 10 to the 8th over 9.8. 0.8.
So 39330.
0.
What's the unit there?
That's going to be seconds.
Okay. Not seconds inverse, it's seconds. The meters are gone.
P
We're
is
dividing
seconds
by
inverse.
per seconds, so it will be just seconds.
So then what makes it seconds inverse?
D.
Okay, so you see how we're dividing by per seconds?
Yeah.
1 over seconds, flips it and puts it in the top. So it's just seconds, right?
Yeah.
Period is how long it takes to go through one full cycle. That's just time. Frequency is how many times you go around per unit of time. So that is divided by seconds, okay? This is a period, so it's just seconds. All right, but this is 39,330 seconds. That's a ridiculous unit for this number.
Man, 655 minutes.
Okay, 655 minutes. Still kind of a crazy unit for this number.
27 hours.
27 hours. Is that right?
Really?
I don't think so.
I was thinking
Well, I
somewhere
took
around
that
like
number
10
divided by
and
60.
55 minutes.
Yeah, divide by 24. Did you divide by 24?
Yeah.
655 minutes is 27 hours?
I don't think so.
Oh, what did it wrong?
655 minutes divided by 60
Oh, I got to divide by 60 to get hours.
to get hours.
Okay. Yeah.
My bad.
Uh-huh.
10 point.
10.9. So
Yeah, that's a little better. More like 11 hours, right?
11 hours.
Okay, so this is a unit that makes sense for that number now, right?
That's why we see the moon in day.
Okay, no. So what's the moon's actual period? Do you guys know?
10 hours.
No,
Somewhere around 12,
no,
13,
24.
14.
no,
15 hours.
no,
117.
no,
8 hours.
no.
1, 2,
No.
3.
Oh my God, stop.
17.
The moon goes through one full cycle from like new moon to new moon.
Oh, 28 days.
28 days.
I thought you were saying it like when it goes,
Yeah.
around the earth.
I thought it was like night and day.
Yeah, that is how long it takes for the moon to go around the earth.
Oh, it's just
Then
because
how
we're
come-
spinning.
We're rotating.
Oh my gosh.
Oh, so if we were standing still.
If we sat still, it would take the moon 28 days to go completely around us. Okay, but we are rotating, so it looks like the moon is going around once a day, but it's not. We're going around once a day.
You know what I want to
The
invent?
moon
Cole?
rises about 50 minutes later every day,
A
or
machine
earlier.
that rotates
Which
the
one is
opposite direction of the Earth's
So
orbit
then
at
what's
the
the
speed
11
of the
hours?
Earth's orbits.
If
So you can
Yeah,
have always
so-
night.
We calculated 11 hours,
And you can sleep.
but actually it's 28 days.
Earth's polarity.
so then it's got to.
That's a huge difference, right?
Yeah.
So explain what happened. Why is there such a huge difference between the two?
Because we were spinning in the opposite direction. as
No.
The moon is spinning around.
What did we screw up? We did something a little wrong in our calculation. What was our error?
We forgot to take into account.
Oh,
our
it's because
orbit.
it's not actually circular. We made it circular.
No, it's basically circular, and that approximation was fine. That wouldn't make it so far off.
It's
The average distance.
Because
No,
okay, darn.
Mm.
Because it doesn't actually have the full 9.8 meters per second.
That's it.
Oh.
The farther away you get from Earth, the radius away from Earth, the less gravitational influence Earth has. So out at 3.84 times 10 to the 8th meters, millions and millions of meters away, our gravity out there is not going to be 9.8 meters per second squared.
That's why when you jump on the moon, you can like hop really
Well, no, that's moon's gravity.
Oh.
That's different. But our Earth's gravitational influence on the moon is going to be significantly less than 9.8 meters per second squared out there. So that's what happened. Okay. So we cannot do this calculation like that. There's
Does gravity-
something different.
Does gravity warps space?
No, that's not it either. There's just a different formula that we have to use to make that calculation. And that happens in the next section. So this section is over.